Hello everyone, I'm Shi Feng from Tsinghua University. This is a joint work, Combinatorial Causal Bandits, with Professor Wei Chen from Microsoft Research Asia. Let's start with the background. Our main topic, Combinatorial Causal Bandits, is a combination of three domains: causal inference, combinatorial optimization, and multi-armed bandits. The intersection of online learning and combinatorial optimization is shown in this slide. Actions, or superarms, are combinatorial objects instead of a single arm. We can find practical examples like route communication and news recommendation. Because the action space is large, the reward of them cannot be fully explored, so we need more techniques. Actually, to do this, we can use feedback at the base arm level. For instance, we can get delay feedback on every row segment or click-through feedback on every news piece. Now, we focus on our combinatorial causal bandits model. The graph may have both hidden and observed binary variables. Y is the target reward. The graph structure is known to the learning agent. However, the probability distribution from parent nodes to a child node is unknown, so we have to learn causality. In each round of our CCB problem, the learning agent can select at most k variables to intervene. For simplicity, we denote do st equals 1 as do st. The learning agent can observe the sample values of all observed variables. Our goal is to maximize the cumulative reward on y, or minimize the cumulative regrets. Two applications of CCB are parameter tuning and drug testing. In detail, in tuning performance of a large system, one often needs to tune a large number of parameters simultaneously to achieve the best system performance. And in drug testing, a combination of several drugs with a number of possible dosages needs to be tested for the best results. We first present a CCB algorithm for binary generalized linear models. In general causal graphs, there is exponential number of parameters that define the conditional distribution from x parents to x. Our binary generalized linear model defines the conditional probability by the linear combination of parent nodes and the function fx on it. In detail, theta x star is the weight of all edges pointing to x, and fx can be exponential function, linear function, and many other functions. BGLM is similar to general threshold model in the social network literatures. When fx is the exponential function, BGLM is equivalent to the independent cascade model. In the CCB problem, the learning agent needs to learn parameters theta x star. There are mainly three challenges of BGLM CCB problem. The first one is how to learn theta parameters. The second one is optimization challenge. Because we are designing online learning algorithms, we need to find an optimal intervention that is retrieved from a confidence region of the estimated parameters. The last one is the exploitation trade-off. For exploration, we have to try different intervention sets for better learning. For exploitation, we need to keep intervene on current best intervention set for better optimization results. It is possible to do both of them optimally and simultaneously. The question is how to balance the two. Our approach is applying maximum likelihood estimation on BGLM and using an MLE based on pseudo-log likelihood to estimate the parameter thetas. You can refer to our paper for details. About optimization, it may not be computationally efficient, but we develop an optimization based on multipliers. For the exploration-exploitation trade-off, we apply the OFU principle. It means that we compute confidence region, maybe an ellipsoid or a circle, of the parameter estimate to cover the uncertainty. Then we optimize both the intervention set and the parameter setting in this confidence region. We have several assumptions for the BGLM-OFU algorithm to get theoretical regret guarantees. The first and second order derivative of fx are upper bounded, and the first order derivative is furthermore lower bounded by kappa. Moreover, we have an assumption to ensure that when all parent nodes of X are fixed, the remaining parent node still has some randomness. Our algorithm uses T0 runs to get a not bad estimation of thetas. Then we apply MLE in each run to update the estimation of thetas. We compute confidence ellipsoid for every X and find the best parameter setting with optimal interventions to maximize Y. Then we do intervention on ST. The idea is very simple, but we give us theoretical proof of the expected regret bound. The regret is O square T log T. The constants rely on the graph size and our assumptions. Our regret bound is polynomial for these constants. In our proofs, the main technical issues are listed in this slide. For the learning part, we need to show MLE is accurate enough and derive confidence region bound. Also, we need a group observation modulated bounded smoothness condition to show that a small parameter change will lead to a bounded reward change. With these two steps, one could imagine that the rewards of all interventions are estimated accurately, so one could find the optimal super R. Next, we consider binary linear models. For the linear model, our algorithm and regret bound apply a large class of models with hidden variables. Condition is that as long as a hidden variable is not pointing to both an observed S and an observed descendant of X via hidden path. Our approach is to convert the causal graph into an equivalent graph without hidden variables. Then apply BGLM algorithm. Conversion is possible due to the linear relationship and relies on due calculus. Furthermore, we can use linear regression instead of MLE. This can remove the assumption on parameters. Also, this algorithm works for linear model with continuous variables, not binary. We also run several simulations. We run a simulation on a parallel BLM. You can see that BGLM-LR algorithm based on linear regression gets the best regrets. Both BGLM-LR algorithm and the BGLM-OFU algorithm get better regrets than traditional bandits algorithms. The difference of performance is huge. CMAB framework cannot be applied to this problem because of the lack of the independence assumptions. Therefore, our algorithm is currently the state of art. We also run simulations on other graph structures in our paper. And last, we introduce some possible future work in this topic. For the BGLM model, one can explore how to remove the assumptions and deal with the hidden variables. Moreover, our optimization step by OFU may be improved to more computationally efficient ones. For the linear model, one could consider removed condition on the graph structure for hidden variables. How to apply CCB to other models is also a future work. Recently, we are working on causal bandits without the causal graph. This is also an interesting topic. Finally, thanks a lot for your watching.